Hello everyone. I'm going to briefly introduce our latest work, Global Placement Exploiting Soft 2D Regularity. Our method is specially designed for the systolic array and 2D array. Systolic array has different applications, like CNN computing, signal processing, and communication circuit design. This is the reason why it becomes popular these days. And on the left-hand side figure, it shows that systolic array generally consists of a 2D array. And on the right-hand side, it shows that for the different type of the systolic array, they may have the different PE structure inside. And then let me introduce our problem formulation. We are aiming to solve the placement problem for the circuit design with 2D array. And the objective is to minimize the half-parameter variance. In this work, our main contribution is to put forward the first global placement technique, exploiting regularity of 2D arrays. Here, let me show you the overview of regularity-aware placement. This placement method is building upon replace. Here, on the left-hand side of the figure, I list 6 steps. The first 4 color steps are using our own techniques, and the last 2 steps are from replace. In step 0, we determine the P array orientation, and then we run the step 1 template assist quadratic placement. The template here represents the intra-PE placement. We use this template for each PE identically and repeatedly. And in the step 2, we run the replace with soft regularity constraints. The regularity constraints here means we need to align all the center of PEs in each row and columns. The soft regularity constraints means that we transform the constraints into the penalty in the objective functions. And then this is step 3. We run the replace with array regularization. This is deeply introduced on the right-hand side. At the beginning of each iteration, we perform the P array regularization first. In this step, we make sure that all the P satisfy the regularity constraints. And on the second line, we calculating the gradients for the E-force and variance. In step B2, we take the advantage of 2D arrays. And in this way, we accelerate this procedure. On the third line, replace adopts the enhanced natural method to solve this nonlinear programming problem. And then we obtain the new solution. If the density of this solution is small enough, we will terminate this step, otherwise we will run it again. And in the first step, we run the replace itself. And finally, we'll do the detailed placement using NTU3 as a detail placer. Then let's have a look at the placement illustration. There are 4 figures. In figure A and B, they are using our own method, and in figure A, it shows the global placement layout. In the figure B, it shows the detailed placement layout. In figure C and figure D, it shows the placement result using replace. In figure C, it shows the result in global placement stage, and in figure D, it shows the result in detailed placement stage. It's obvious that our method can generate the layout with better regularity compared with replace. Here is our conclusions. We found that considering the regularity of 2D array improves the placement quality. Using our own method, Health parameter wear length and routing wear length are reduced 8.3% and 11.0% compared with replace. And health parameter wear length and routing wear length are also reduced by 8.4% and 8.2% compared with structural wear placement. Thank you for your listening.